We're building a CNC tube coping machine as part of our multidisciplinary senior design project with the Kate Gleason College of Engineering. This device will notch metallic tubes so that they can be assembled and welded. Let's meet the members of our team.
Hi, my name is Jay. I'm a fifth-year computer engineering student.
I'm Lisa. I'm a mechanical engineering student.
Hello, my name is Joe Cachera, and I am a mechanical engineering student.
I'm Joe. I'm a mechanical engineering student.
Hi, my name is Malcolm Sherman Godfrey, and I'm an electrical engineering student.
Hi, my name is Tolly Weinstein, and I'm a mechanical engineering student.
When we first got this project, the current state was that the RIT machine shop didn't have a dedicated tool for coping tubes. So our desire by the end of the project is to build a dedicated tool to help cope tubes and make one that's cheaper and easier to store than what is available commercially on the market. So kind of the core goals of the project are produce a functioning machine that fulfills the different customer requirements, meet safety standards so that the machine is safe for students and staff to operate, ensure that the machine is documentation so that even after we graduate, the machine can be used by a variety of different people, and preferably that it's both easy to set up and quick to learn. And then also that this device produces high quality copes for use on future senior design projects, project teams, and a variety of other students and professors who use the machine shop. A couple of the constraints is to keep the machine under 250 pounds, to keep it more mobile, to keep the footprint under 48 inches by 36 inches so it doesn't take up too much storage space, and to keep the costs under $750.
So our MSD project was initiated as a means to provide a more efficient and user-friendly in-house method of notching metal tubes in the mechanical engineering machine shop here at RIT. Seen below is the current method for cutting tubes, which utilizes a 3-axis Bridgeport mill in conjunction with a rotary table and collet block to allow users to notch a wide range of tube diameters, lengths, and materials. This current method has many downsides though, as it is very time-consuming to set up and tear down, usually requiring multiple people, while potentially also taking up a mill for days or weeks at a time when in use. The machine is also not user-friendly, requiring the user to be in an unergonomic position due to its mounting methods and size. Further, this setup has a steep learning curve to use, requiring a significant amount of experience to operate safely. This project has been proposed to create a standalone machine that is safer to operate by users of varying skill levels while requiring substantially less setup and runtime than the current method.
The system architecture has been determined following the concept generation that we did during MSD1. To hold the tube, we decided to utilize a 3-jaw chuck since the shop already has a few of these around. The plasma cutter was selected because of its ease of use, general safety, and most importantly, reasonable cost. We decided the microcontroller would read in G-code and parse it into the machine motion. The Technic ClearPath motors were selected because of their open source library for motion control, closed loop servo design, and ability to get the motors sponsored. Some highlights of our system architecture are the safety switch, or e-stop, will cut the machine power if the machine crashes or the user hits the button. Additionally, our plasma cutter is able to be powered off of a common 120-volt outlet, which means it can be placed almost anywhere in the machine shop.
Here are some screenshots of the machine design in Creo. The frame is constructed of 2-inch steel box tube, and it has a footprint of 36 inches by 20 inches by 12 inches. It can be collapsed down to 30 inches by 11 inches by 12 inches for storage. The plasma cutter is mounted on a 15-inch THK linear stage, which is driven by a Technic ClearPath servo motor. The drivetrain also has a Technic ClearPath servo motor, and that's used to rotate the chuck, which rotates the workpiece. There's a 2.5-to-1 ratio between the motor and the chuck. So the chuck rotates the workpiece, and the linear stage moves to cut the desired profile into the workpiece.
This image shows the block diagram of the electrical hardware system of our machine. This system includes elements executing functions such as user input, control, system monitoring, and power. The primary element of our electrical hardware system is the Arduino Mega, which is the microcontroller we have selected to run our system. This microcontroller receives user input in the form of G-code loaded onto an SD card, which our software then converts into commands recognizable by our Technic motors. The Arduino Mega also controls whether or not the plasma cutter is active, that is, whether or not it's able to cut using a trigger control system. The Arduino Mega receives feedback from the Technic motors and compares that against what lines are being executed in the code so that it is able to detect an error and also update the system status LEDs, which indicate to the user whether the system is in a ready, active, or error state. An additional safety feature integrated into our electrical system is an emergency stop button, which, when pressed by the user, will send a signal to the Arduino, disabling the motors and plasma cutter and ensuring that the user cannot come to harm. All of these systems are powered from a 120-volt AC wall outlet, which is fed through various adapters for the various elements of our system, including a 9-volt adapter for the Arduino and a separate power supply for the Technic motors.
We can see on the software flowchart that there are 6 functions: system status, run motors, parse G-code, stop machine, update LED, and cope tube. The system status function just gives an overall status of the entire machine. Run motors runs or stops both the motors. The parse G-code parses through the G-code file and runs and executes each G-code line through the Gerbil library in the Arduino. Stop machine stops the machine in 3 situations: if the coping is done, if there's an error produced, or if the e-stop is pushed. Update LED updates the LED based on situations such as the LED turns green if the machine is idle, the LED turns yellow if the machine is on, and the LED turns red if the e-stop or an error is produced. Cope tube just copes the tube and shuts the machine down.
Currently, we're working on assembling the different systems, manufacturing individual parts, testing different components, and developing and testing our electronic systems. Finally, we'd like to thank our project sponsors, without whose help we wouldn't be able to complete this project. So thank you to Technic and PrimeWeld for donating materials to our project. And also thank you to everyone watching this for wanting to learn more about our senior design project.